previous lecture, we have started a new unit of the course on the topic of algorithms and methods for solving linearly constant nonlinear optimization problems. We have discussed in the previous lecture three particular methods. Those are active set method, projected gradient method, and the reduced gradient method. Now in this lecture, we are going to discuss one more method, interior point method, for solving a special class of linearly constrained problem, that is the quadratic programming problem. So this lecture is on the topic of interior point method for constrained quadratic programming problems. You know, the interior point method was not initially evolved for solving quadratic programming problems. It was basically evolved for solving linear programming problems. It actually came out from the quest among optimization specialists that can we have a computationally efficient method for solving linear programming problems that can beat the computational efficiency of the simplex method. And it was the year of 1984 where the interior point method was found, and it brought a complete revolution in the literature of optimization, and for which there was a headline in the newspaper, the New York Times. The headline on the front page was breakthrough in problem solving. The breakthrough idea in the interior point method was 2 points. The first point was that interior point method is basically a nonlinear programming technique to solve linear programming problems. The second point is that unlike the simplex method, that simplex method moves from one vertex to the another vertex of the polytopic region, the constraint set of the linear programming problem, to reach at the optimum solution. Unlike the simplex method, the interior point methods move from the interior of the feasible region to reach at the optimum solution. Due to these 2 points, it was found that the simplex method can be beatable and the interior point method is computationally efficient and better than the simplex method. And learning this computational efficiency of the interior point method for linear programming problems, later on this interior point method was evolved for general constant optimization problems. Now in this lecture, we are going to discuss the interior point method for solving constrained quadratic programming problems. Let's start. To discuss the interior point method for quadratic programming problem, we consider the statement of the quadratic programming problem as follows. That as usual, we are to minimize a quadratic function. Let's suppose the quadratic function is denoted by qx with the usual expression where this capital G is a symmetric matrix and positive semi-definite, and the vector G is a given vector in the n-dimensional Euclidean space. We have to minimize this quadratic function subject to a set of linear inequalities given by ax minus b is greater than or equals to 0. Here, as usual, the vector x is the generic variable vector and x is belonging to the n-dimensional Euclidean space Rn. Now to find a solution of this quadratic programming problem, we notice that this optimization problem is optimization of a convex function subject to a set of linear inequations. And for linearly constrained convex optimization problems, you know, a generalized version of the Abadi constraint qualification or a generalized version of the Arrow-Hurwitz-Ujoa constraint qualification is automatically satisfied. So an optimum solution to this quadratic programming problem is a KKT point. The KKT optimality conditions for this optimization problem are given by the first condition is the stationarity of the Lagrangian function, which you notice that the gradient of this qx plus some lambda times summation of the gradient of all gi's, and that will be equals to 0. And this equation of stationarity gives us the gradient of Qx, that is Gx plus small g, then plus lambda times the gradient of all these constraints. Here you need to write all these constraints in the less than equal to form, and accordingly you will get that minus A transpose lambda is equal to 0. Then the primal feasibility condition in the KKT conditions is that your constraints Ax minus b greater than equals to 0. The dual feasibility condition is your all these Lagrange multipliers, which are essentially the dual variables, they are greater than equals to 0, and complementary slackness condition will give us the slack variables for these constraints. If I just go for writing y as your Ax minus b, and that will give us the slack variable vector. Component wise, the slack variable vector, and component wise you consider the components of these lambda. Component wise of this y and lambda, their product will be equals to 0. That is your complementary slackness condition, and hence in the complementary slackness condition you will have yi times lambda I is equal to 0 for every I is equal to 1 to till m. Here we are considering that this matrix capital A is a matrix of order m by n, and here we have the vector b belonging to the m dimensional Euclidean space Rm. Then you will have m many Lagrange multipliers and m many slack variables, and accordingly here you will have m many equations in the complementary slackness condition. So here in totality these four conditions will give us the KKT optimality conditions. As we have already introduced the slack variables here, so here we can just go for replacing these inequations by the equality that Ax minus y minus b equals to 0, and here you take the restriction that y greater than equals to 0. That means the primal feasibility condition will have now two components, one equality constants together with y greater than equals to 0. Now to find a solution of this quadratic programming problem, we are to find a solution of this system of equations. Note that this system of equation has linear equalities here, linear equality here, linear inequalities here. Here also goes linear inequalities. So this system is going to be a set of linear equations and inequations, but just by the presence of these nonlinear equation, this entire system, this entire KKT system is a nonlinear system of inequations and equations. Then whatsoever be the case, so whether or not this is a system of linear or nonlinear equations, we have to find a solution of these KKT conditions to get an optimum solution of this quadratic programming problem. So let us now try to find a solution of these KKT conditions. To find the solution of this system of inequations and equations, we have found that we have presence of nonlinear equations. So before jumping to get a solution of these KKT conditions, let us just get a geometrical observation, a geometrical perspective of this condition, the complementary slackness condition, and then we will get into with the deeper details of solving this system of KKT conditions. We notice that apart from just these equations, we have a set of linear equations and linear inequations, right? And we all know the intersection of linear equations and linear inequations essentially give us a polytopic region. Let us suppose the polytopic region given by the set of these KKT conditions except the complementary slackness condition is giving us hypothetically, let's suppose, a polytopic region of, let's suppose, this kind. So this is the region, a polytopic region given by this set of equations and inequations. Let us suppose these set of equations all together, they are collectively giving us a geometrical region, and that region it is denoted by C. So C geometrically is this set. Now we notice that inside this complementary slackness condition, we have yi times lambda I is equal to 0. So either yi is equal to 0 or lambda is equals to 0, or both of them are equals to 0, right? Now, to obtain a geometrical sense about the complementary slackness condition, let us suppose for the time being, just to obtain a crude analysis about the complementary slackness condition, we just consider that m is equal to 1. That means you just only have only one constraint in the given problem. Now, when we have m is equal to 1, then we see that this complementary slackness condition will have just only one restriction, y1 into lambda 1 is equal to 0. Now, let us suppose we have the value of y is equal to 0. Then you notice that the corresponding component here in this equation will give us ax is equal to b. Similarly, when lambda I is equal to 0, we look at this equation, and here we see that corresponding to lambda I is equal to 0, we will get here gx plus small g is equal to 0. So essentially yi times lambda I is equal to 0, here altogether these complementary slackness conditions will figure out a point x y lambda inside the set C, for which ax is equal to b, and therefore corresponding to a point that satisfies this complementary slackness condition, we are crudely satisfying gx plus g is equals to 0 and ax is equal to b. And we notice that these sets of linear equations, they essentially finds out these vertices, intersection of the hyperplanes, those are given by these two equations. And therefore we notice that uh, for whatsoever points x, y, lambda in C, once the complementary slackness condition is satisfied, we are essentially on these vertices. So a KKT point, a point x, y, lambda that satisfies all these conditions essentially lies on the boundaries, and more specifically on these vertices of the feasible region capital C, given by this set of linear equations and inequations. Well, after finding this very crude analysis about the complementary slackness condition, let us now look the problem mathematically. In the concrete mathematical manner, let us now try to solve this KKT system to find a KKT point of the given optimization problem. To find such a point xy lambda belonging to C, as well as that satisfies the complementary slackness condition, we look at this KKT system of equations and inequations, and then we figure out that it is essentially equivalent of finding a root of the equation if x y lambda is equal to 0 together with y greater than equals to 0 and lambda greater than equals to 0, where this function f is given by from this stationarity condition, we have the first component of this equation as your gx minus a transpose lambda plus g. The second component is here, this equation ax minus y minus b, and here now these complementary slackness conditions, we are writing it out in a vectorial form or in the matrix form by y times lambda e, where capital Y is equal to a diagonal matrix consisting y1, y2 till ym. Lambda is also a diagonal matrix whose diagonal entries are lambda 1, lambda 2 till lambda n, and E is a vector in the m-dimensional Euclidean space. a column vector where all components are 1. Sorry, we have here many components lambda m, and accordingly this vector E is also having many components. We notice that this is a very special way of writing all these equations, complementary slackness equations, that yi lambda I is equal to 0. Now if we consider this y lambda E is equal to the null matrix, the 0 matrix, then you notice that this y lambda E essentially gives us a column vector consisting the first component as y1 lambda 1, second component as y2 lambda 2, and the mth component is ym lambda m, and therefore y lambda e is equal to the 0 matrix essentially involves all these m equations in the complementary slackness condition. So this entire KKT system is equivalent of finding a root of this equation f is equal to 0 together with the conditions that y greater than equals to 0 and lambda greater than equals to 0. Now here a question would come, how to find the solution of this equation. This is a vector equation. It is not just a equation of on both the sides we have real numbers. It is not like that. It is a vector equation. We have many components in capital F, and therefore to find a solution of this equation we can go for employing one of the root finding methods, like you may employ the Newton's method to find a root of a nonlinear system of equations. Notice that the Newton's method to find the solution of these nonlinear equations is iteratively find a sequence xk, yk, lambda k, where this sequence is given by starting from an initial point x naught, y naught, lambda naught. You go for solving at the kth iterate the equation given by the Jacobian of the function f at the point xk, yk, lambda k times delta x, delta y, delta lambda is equal to negative of the function value at xk, yk, lambda k. This is your Newton scheme, that you start from one initial point x naught, y naught, z naught, then go for finding iteratively the k plus 1th iterate given by the kth iterate plus this vector delta x, delta y, delta lambda, where delta x, delta y, delta lambda is a solution of this equation. We note that here in the left hand side of this equation is the Jacobian of the function f. We recall here the Jacobian for this function here. We all know the Jacobian of vector valued function that has a p many components f1x, f2x till fpx is given by the first component as the gradient of f1 its transpose, that is your first row. The second row is the gradient of the second component of the function capital F, that is gradient of f2x its transpose, and you will end up with the pth component gradient of fpx its transpose. That is your Jacobian of vector valued function. Now here for this function capital F, which is given by this expression, the Jacobian will give us the matrix that this matrix where this capital Y has to be evaluated at these vector yk. So let us also denote here yk, here also capital lambda k. Capital Yk is a diagonal matrix whose diagonal entries are the components of this Yk. Similarly, for lambda k, it is also a diagonal matrix consisting the diagonal entries are all components of this lambda k vector. Now, if we plug this expression over here, then we will find that the Newton scheme or Newton method to find a root of f x y lambda equals to 0 is given by solve this set of linear equations and find delta x, delta y, delta lambda, and then update the iterative point by xk plus 1, yk plus 1, lambda k plus 1 is equal to xk, yk, lambda k plus delta x, delta y, delta lambda. So this is your precisely the Newton scheme, the Newton's method to find a root of this f x y lambda is equal to 0. So here you use the Newton's method to find this sequence xk, yk, lambda k, and maybe a limiting point of this sequence is going to give us a solution of this equation. But you notice that a limiting point of this sequence is going to be a solution of this equation is assumed only when certain conditions of the Newton method is satisfied, right? Like the initial point has to be very close to a root of the equation, and this is a major crucial drawback of the Newton's method. But not only this, you notice that Newton's method has also several other drawbacks. Then what could be a possible way out? That we cannot just directly go for solving this equation by the Newton's method. So here what we do is that instead of exactly solving this equation, we go for taking an approximate version of this entire KKT systems, and just by solving that approximate version of the KKT conditions, we slowly go for finding a solution of this entire system exactly. Now here what we do to formulate an approximate system of these KKT conditions, we have found that this complementary slackness condition is a bit crucial, that it is the only equation which is nonlinear, and this condition is possibly the most difficult condition. That is that it is a combinatorial condition, like if yi, you check whether yi is greater than 0 or not. If greater than 0, then we need to take lambda is equal to 0, or if lambda I is greater than 0, then we have to take yi in such a manner that yi has to be 0. So these actually gives us a bit of combinatorial difficulty. So what we do, we consider this 0 to be revised by a certain positive quantity, and then slowly reduce this positive quantity to 0. So here we are going to approximate this entire KKT optimality conditions just by revising the right hand side of the complementary slackness condition by certain positive quantity. Here we notice that revising this right hand side 0 of the complementary slackness condition by certain positive quantity will sort out the combinatorial difficulties of the complementary slackness conditions. And now if we revise this 0 by some positive quantity. Let's suppose we are revising it by some tau. Tau is greater than 0. Then with a given value of tau, go for solving this entire system approximately for a given value of tau, and we will proceed. To proceed further our discussion, let me neatly write at first this entire set of approximate KKT optimality conditions. By approximate KKT optimality conditions, I mean you replace this 0 by tau. Let me neatly write out these approximate KKT conditions, and then I will go for further discussion. Otherwise, the discussion will not go in a neat manner. The approximate KKT conditions for a given value of tau greater than 0 is given by this set of equations together with here component wise y and lambda, they are non-negative. Now here let me make a nomenclature that a solution of these KKT conditions, these approximate KKT conditions, let's suppose it is your x tau, y tau and lambda tau, and then for different values of tau you collect all these points and we name it as capital C, and we shall refer this set C, which obviously finds out the trajectory of the solutions for different values of tau in these approximate KKT conditions. This trajectory we name as the central path. Let us name these approximate KKT conditions as let's suppose I name it by 1. A solution to 1 for a given tau is given by x tau, y tau, lambda tau, and the collection of all these points for different values of tau is named as the central path. And why is it named as the central path? The reason is as follows. We notice that the feasible set, the set capital C, that we have drawn and figured out earlier, that the feasible set capital C is given by a polytopic region, like let's suppose this polytopic region, which was named as the set C. The capital C was named earlier over here, and this set capital C I am now again redrawing here in this figure. Oh, sorry, I have also named the central path as C. So let us name these then feasible set, earlier feasible set, as by some other name, let's suppose F. Then there will be no confusion, otherwise we may get confused with this set capital C, which is the usual notation for the central path. So let us keep intact that C as usual in the denotation of interior point methods. So here C is denoting the central path, and here is your feasible set capital F. We notice that here these complementary slackness conditions, these approximate complementary slackness conditions, geometrically gives us a line in the y lambda space. Let's suppose this is your axis of y1 lambda 1, and this is your axis of y2 lambda 2. Then we look at these equations, we see that these equations are saying y1 lambda 1 is equal to tau is equal to y2 lambda 2 is equal to y3 lambda 3, and so on till is equal to ym lambda m. So here we notice that then y1 lambda 1 is equal to y2 lambda 2. So these approximate complementary slackness conditions, they are essentially giving us this line y1 lambda 1 is equal to y2 lambda 2, right? And these line in the feasible set gives us an image in the feasible set, let's suppose this part, And we now look at the points in this central path. We notice that the points in this central path are those points which are solutions to these equations 1, right? And therefore y tau lambda tau must be satisfying. Their product is equal to tau, and therefore any point in the central path, they are lying in this straight line, and hence in this feasible set the corresponding points, they are lying on this particular trajectory, and this particular trajectory then consists of those points in the feasible set capital F, for which the points are lying over here in the y lambda space. And when y lambda, these values are approaching towards 0, then you notice that these points on this path, they are actually approaching towards this particular point, which is essentially corresponding to this point in the y lambda space. And this point, you notice that is nothing but the point for tau is equal to 0. And precisely you wanted to find a solution to the original KKT system, and original KKT system is your this approximate KKT system with tau is equal to 0. So just by following this path in the y lambda space, you are essentially following this curvical path. That means the points over here, which is leading us to the solution, a point that satisfies the original KKT system, right? And that's why these trajectory or this path, which are essentially consisting of the points x tau, y tau, or lambda tau, they are inside this set C. This set is called as, or this path is called as the central path, because this is the path which is leading us to a KKT solution. So by this geometrical observation, what we have observed that then in a degraded manner, you take the value of tau naught something, a big value, then you take the value of tau 1, the next tau value a bit lesser than tau naught. So in a degraded manner, you take the tau values, and accordingly you generate solutions of this system. You find out x tau, y tau, lambda tau. Accordingly, in the feasible set, you are approaching towards the solution. So the idea here is that you generate a sequence tau k which decrease to 0, and accordingly you find out solution of this approximate KKT conditions, and in the limiting case you are essentially reaching at a point that gives us a KKT point. Now here you might ask that if we are solving out this approximate KKT system for different values of taus, why not to just take tau is equal to 0 and go for solving it? The answer to this question would be as follows. Yes, you can be aggressively taking the value of tau is equal to 0 and go for solving this equation. Then obviously you are going to reduce to the same problem, that you are going to employ the Newton's method directly on the KKT system, and then you will face the difficulties. Those are there for the Newton's method. But then you might ask, then what method then I am going to employ for solving these approximate KKT condition for different values of taus? Am I not going to use the Newton's method to solve it? Yes, actually we are going to use the Newton's method to solve it, but we will not directly solve this system for every value of tau, but rather for a given value of tau, let's suppose tau k, we will just take one iteration of the Newton's method for this approximate KKT condition, and then in the next step we consider the revised value of tau k, and that is your, let's suppose, tau k plus 1. Then for tau k plus 1 you form these approximate KKT conditions and take just one iteration of the approximate KKT condition for tau k plus 1 to find out the next iterative point xk plus 1, yk plus 1, lambda k plus 1, and move forward. So here what we do, for every given tau k value, we are just going to consider one iteration of the Newton scheme for the approximate KKT condition. We are not going to solve for each and every value of tau k this entire system. We are just going to consider one iteration of the Newton's method for these approximate KKT condition. And the process is as follows. Let me write out that we take one iteration of this system 1 to find a sequence of iterative points. We start our process with a given visible point x naught, y naught, lambda naught that is belonging to the interior of the feasible set. By interior of the feasible set, I mean the following set, that you consider all the equations here, but you replace here this y lambda, these components are all greater than 0. So here your f naught is the set of all points x, y, lambda such that you have gx minus a transpose lambda plus g is equal to 0, ax minus y minus b equal to 0, together with yi lambda I is equal to tau for all I, as well y greater than 0 and lambda greater than 0 component wise. This is your set f naught. Start with a point x naught, y naught, lambda naught from f naught. Then to find the next iterative point, or let's suppose xk plus 1, yk plus 1, lambda k plus 1, we take one iteration of the Newton scheme for the approximate KKT conditions 1 with tau is equal to tau k. That means we go for solving. This step essentially means that we go for solving the following Newton scheme for lambda delta x, delta y, delta lambda, where we notice that the Newton scheme for these equations in 1 is given by your f tau x y lambda is equal to 0 with y greater than equals to 0, lambda greater than equals to 0, where your f tau, this function x y lambda is equal to, we will have here the first component as these equations, second component as these equations, and the third component is now in the matrix form. We notice that these equations can be written as capital Y capital lambda E is equal to tau E, where as usual capital Y is the diagonal matrix having diagonal entries are y1, y2, y3 till ym, and similarly for lambda. So here this third component of f tau gets the expression y lambda E minus tau E. This is your f tau, this function. Now for this function, the Newton scheme gives us the Jacobian of this function times this delta x, delta y, delta lambda is equal to negative of this function, which will give us this matrix. This matrix is your Jacobian matrix of the function f tau times delta x, delta y, delta lambda is equal to the negative of the function, that is your this vector, a negative of it. we need to solve this equation at the point xk, yk, lambda k to find the next iterative point xk plus 1, yk plus 1, lambda k plus 1. That means you go for plugging here the values of y at yk, lambda at lambda k, x at xk. You find the solution of this equation and then take the next iterative point as the previous iterative point plus this delta x, delta y, delta lambda. So this is how we proceed. We go for solving this equation for the current given value of tau. Tau is equal to tau k, and you notice that we are solving this equation just once. It is not that iteratively we are just solving this equation and finding out the sequence xk, yk, lambda k. It is not that. We are not actually finding a solution of these approximate KKT conditions for a given value of tau is equal to tau k. But rather for the given value of tau k, we are considering the equations in the Newton scheme. This equation, find out delta x, delta y, delta lambda, get the next iterative point xk plus 1, yk plus 1, lambda k plus 1 given by this equation. Then again go for revising this tau by some next value tau k plus 1, and then accordingly you find delta x, delta y, delta lambda for the point here. You consider yk plus 1, lambda k plus 1, here also xk plus 1, lambda k plus 1, and so on, and then find the next iterative point xk plus 2, yk plus 2, lambda k plus 2. Therefore, notice that to find the consecutive iterative points, we are not actually solving this system for over and again for the same value of tau. We are revising the value of tau at each iteration, and we are not actually crawling around the Newton scheme only for a given value of tau. That is, for a given value of tau, we are not aiming for solving this system, but we are just considering the Newton scheme for this system and solve the Newton scheme for this system only at the point xk, yk, lambda k with the value of tau k to find the next iterative point xk plus 1, yk plus 1, lambda k plus 1. Then after obtaining the next iterative point, you consider a revised value of tau, a lesser value than tau k, then go for finding the next iterative point xk plus 2 and so on. So in a decreasing manner of tau k, you go for taking just one iteration, just solving this equation only once. It is not that iteratively we are solving the same equations over and again for the same value of tau. So it is not that we are applying here the Newton's method, the fully Newton's method to find a solution of the approximate KKT conditions for a given value of tau, and thereby we are depending on this Newton scheme, but we are not fully using this Newton scheme just to solve the approximate KKT conditions for a given value of tau. But when we aggressively take the value of tau is equal to 0 and then go for solving this system, then you will face difficulties of the Newton's method. But here in this process to generate the sequence xk, yk, lambda k, we are just using the Newton scheme, these equations, to find the consecutive iterative points. We are not solving these equations over and again for the same value of tau. So to find a solution of the original KKT system, what we do, that we take a value of tau naught and take an initial point that is lying in the set f naught, then take just one iteration of the Newton scheme for the approximate KKT system with tau is equal to tau naught. Then find your delta x, delta y, delta lambda. Find the next iterative point x1, y1, lambda 1. Then revise the value of tau from tau naught to some value tau 1, which is smaller than tau naught. Then take one iteration of the Newton scheme for the approximate KKT conditions for tau is equal to tau 1. Find the next iterative point x2, y2, lambda 2, and in this manner you proceed further. And accordingly, you will generate a sequence of points xk, yk, lambda k. Those are obviously lying nearby to this line, not exactly on this line, because we are not exactly solving this entire system for a specific value of tau. We are just taking one iteration to move further, and therefore just one iteration will not give a solution of this entire system for some given value of tau, right? So for a given value of tau is equal to tau k, we are just taking one iteration, and therefore we are getting just an approximate solution of this system. So therefore we are approximately on this line, and therefore we are approximately on this central path. We start from some x naught, y naught, lambda naught. Then next iterative point is somewhere over here. The next will be somewhere over here. So in this manner you will crudely follow the central path, and ultimately you will reach at the solution point. It is expected that we are reaching at the optimum solution point. Now, what is the theoretical guarantee that you will certainly reach at an optimum solution? That means a solution of the original KKT system. That means this system with tau is equal to 0. The theoretical guarantees are as follows. The first result states that on the central path, we certainly have y tau transpose lambda tau is equal to m times tau. This is very trivial because you look at the definition of the central path. In the definition of central path, we have x tau, y tau, lambda tau as a solution to this system 1. And in order to be more correct, this x tau, y tau, lambda tau should be a solution to 1 with, as you need the points, these x, y, lambda are to be feasible points. So we consider here with y lambda greater than 0. So this is the definition of central path. And on the central path, we notice that we have yi lambda I is equal to tau, right? So if I sum it of all these yi lambda i's, you will get on the right hand side m times tau. And that is what precisely I have written over here, that on the central path we have this equation valid, or also you can write the value of tau is equal to 1 by m times yi tau times lambda I tau for the summation I is equal to 1 to m. And also, as tau decreases to 0, we can show that the primal objective function, or the objective function of the given quadratic programming problem, the objective function value will be decreasing in nature. As tau gets decreased to 0, the objective function value will slowly degrade and reach at the optimum solution. So the objective function value on the central path slowly reaches to the optimum solution when t tends to 0. That we have geometrically already seen here, that when we are over here, then obviously we are at a point at which the KKT condition is satisfied, because at this particular point you have tau value is equal to 0, and tau is equal to 0 is going to give us a KKT point. And the result that I have stated over here, that states that as you in a controlled manner you are degrading the value of tau, you are actually reaching slowly towards the optimum solution, the minimum value of the objective function value. The proof for the first part is trivial. For the second part, I will not have time here to prove it, but for a proof, I'll refer you to a very authentic book on interior point method for linear programming, quadratic programming, as well as for convex programming problems. The book by Dane Hertog entitled, you please look at the lemma 2.10 on the page number 36 of this book. You will find a proof of this result. In the interior point method, we actually don't directly apply this result, but we have seen already that we are not actually going to find the points on the central path x tau, y tau, lambda tau, and then take limit tau tends to 0. This is not exactly we are doing, because to find this x tau, y tau, lambda tau exactly, you notice that we have to solve these approximate KKT equations for every given tau, maybe with the help of the Newton's method, and that will be really a tedious and cumbersome process. That for every given tau, you go for finding an exact solution of this system with the help of the Newton's method, and then go for finding x tau, y tau, lambda tau, take limit tau tends to 0. And that is not exactly we are doing. We are not exactly following this central path, but we are approximately solving this system. By approximately solving, I mean I am just taking one iteration of this equation, then I am getting one approximate solution of this equation 1, because just one iteration is not going to give us an exact solution, and therefore in one iteration this equation, this approximate complementary slackness condition, might not be followed by one iteration. So approximately we are over here, and then next alternative point might be here, then next alternative point might be here, and afterwards next might be here, and so on. Ultimately we are reaching at this origin here, and accordingly we are slowly reaching, by following the central path crudely, at this optimum solution at this KKT point. Now here we notice that we are not exactly solving these approximate KKT conditions for every given tau k, and therefore we can just go for replacing this tau by some approximated value of tau, maybe some value, a controlled value of tau, maybe let's suppose some sigma times tau. When sigma is equal to 0, then we are exactly at a KKT point, and when sigma is equal to 1, then we are on the central path. So practically what we do here, we replace this tau by this some sigma times tau, where sigma we control in such a manner that this sigma tau gets degraded as the iteration progresses. That means instead of tau k, we take here some sigma k tau k over here, where tau k is measured by this theorem, that you consider the value of tau k to be this expression at the current iterate, and then multiply this tau k by sigma k, and sigma k is now at your hand. You control sigma k, you degrade it so that sigma k times tau k, that tends to 0 as k progresses. Now you might ask, then how to choose the values of sigma k? This tau k, we can prove that if we follow this process, the process that I wrote over here to find this sequence xk, yk, lambda k, if we follow this process, you start the process with an initial point, then at each and every iterative points, you go for taking one iteration of the approximate KKT system. Then obviously you are going to get a point xk plus 1, yk plus 1, lambda k plus 1. We can prove that if you start your process from a point from this f naught, and if this f naught is non-empty, then the value of tau k given by this summation of yik lambda ik actually degrades. So for a quick degradation of this value sigma k tau k, what do? We choose just one value of sigma k, that is lying in between 0 and 1, and at each and every iteration you keep multiplying this sigma k with tau k, and that gives a mass degraded value of tau k, and accordingly you go for finding out this sequence of iterative points for different values of sigma k times tau k. And here there is a fascinating result, that if the degradation of the sequence tau k satisfies certain inequality, then we can prove that this process of finding the sequence xk, yk, and lambda k, the process that I have described over here, will take the number of iterations not more than a polynomial of the number of inequations to reach at a KKT point of the given problem. We shall state this result neatly towards the end of this lecture, this polynomial time complexity. But before that, let me now neatly write out the algorithm that we shall follow in the interior point method to solve the quadratic programming problem at our hand. The general interior point method for the considered quadratic programming problem. The steps are as follows. At first, we should initialize the process. In the initialization, we need to give the initial iterative point x naught, y naught, lambda naught to find a solution to the original KKT system, that is with tau is equal to 0 for the given quadratic programming problem. That is to find a solution of the system that I wrote at the very beginning. The system is over here. Let us name it as star. We are aiming for solving the system of equations star. And the algorithm to solve this equation star is as follows, that we initialize the process with a given initial point. We also provide in the initialization step the termination scalar epsilon, some number epsilon greater than 0, and this termination scalar is used for checking whether your tau k at the kth iteration is less than epsilon or not. If not less than epsilon, that means we are not close to a solution to star, because for a solution to star we should have the value of tau k approximately equals to 0, right? And therefore when tau k is bigger than epsilon, then you keep computing the iterative points, and when tau k is less than epsilon, you can declare that the current iterative point xk, yk, lambda k is a solution, an approximate solution to star. So we proceed to the main step by initializing the iteration counter k is equal to 0. Then the main steps are as follows. That you compute the value of tau naught, that is given by 1 by m summation y naught I into lambda naught I is equal to 1 to m. We are actually following this formula of tau. That tau is given by this equation. So you just compute the value of tau naught here for the given initial point and check if your tau naught is less than epsilon or not. If not, then you go for finding out the next iterative point, which will be done as follows, that you follow these steps that I have written over here. that to find xk, yk, lambda k, we follow all these steps. And in this step, you have to find a solution of these equations, right? We find delta x, delta y, delta lambda by solving this system of linear equations. So you take here this system of linear equations. This system, but before writing this right hand side, I would like to speak a few words here. That we notice that the initial point, obviously we choose from the set f naught, and f naught is the set of points. Those are in capital F. Capital F, by that we mean this feasible set here, capital F, and this capital F is given by all these set of equation and inequations deleting this approximate complementary slackness condition. And in f naught, I have already written here that f naught is given by all these equations together with these two conditions, that y greater than 0 and lambda greater than 0. So we choose a point from this f naught to start the process, and therefore at the point x naught, y naught, lambda naught, we have here an equality, here also an equality, and this condition we just forget about it, because this condition we are replacing this condition by some tau, by some sigma times tau, right? So we just forget about it to form the set f naught to take a point in this algorithm. And then we see that we have this g x naught minus a transpose lambda naught plus g is equal to 0. This component is also equal to 0, but this component is to be replaced by some sigma k times tau k, right? So here I take now 0, 0, y lambda e minus sigma k tau k e. Here also we have yk lambda k. Now here you might ask that okay, for the initial point you have taken inside f naught and therefore you are keeping these are zeros, but what about the general point xk, yk, lambda k? For the general point, you know, there is a result that if the initial point is taken inside f naught, then by this process that I would be writing in this algorithm, all the next and consecutive iterates, they are also belonging to f naught. That we can prove, and therefore we can safely replace these two components, these and these, on the right hand side equals to 0 matrices. So now you solve this bottom equation for delta x, delta y and delta lambda, then take the next iterative point by this iteration formula, and by computing the next iterative point, you go for computing your tau k plus 1, which is given by 1 by m summation over I is equal to 1 to m yki times lambda ki. You choose your sigma k plus 1, some number in between 0 and 1, and then increase your iteration counter by 1 unit. Then again you go for checking while you have tau k greater than equals to epsilon naught. If not, then you stop and then you give the output that the point xk, yk, lambda k is an approximate solution to the original KKT system with tau is equal to 0. That means the KKT system star, and if your tau k plus 1 is greater than equal to epsilon, then you keep computing all these steps and move further. Here you can also take some step length to be multiplied, like in the damped Newton method. In the damped Newton method, we don't exactly take the full Newton step, but we do multiply with a given step length. And here then you might ask how to choose this step length. For choosing this value of alpha k, we rule in the following manner. Then we notice that we are trying to approximately solving this approximate KKT condition, right? So while taking one iteration of these approximate KKT conditions, what we do? We consider a neighborhood of the central path. How do we consider a neighborhood of the central path? It will be as follows: that at each and every point on this line, you consider a neighborhood of radius sigma times tau. And as you notice that the value of tau gets degraded, so when we will approach towards origin, this neighborhood will give us neighborhood of smaller radius as we approach towards origin, right? And accordingly, this neighborhood will then figure out a region like in between this line and this line. These two blue lines in this visible region will give us two curvical paths, where inside these two blue lines the central path is lying. Fine. And you take the step length in such a manner that in any of the iterations you are not moving out of this neighborhood. Let me draw out this neighborhood afresh. Then we can understand the thing better. Or let me just write out the neighborhood that is commonly considered in the path following methods, in the interior point methods. To find the value of alpha, we follow the following process: that take alpha in such a manner that the point xk plus 1, yk plus 1, lambda k plus 1 that belongs to a neighborhood of the central path. Commonly we take in the short step path following method, which for a given value of sigma is given by the set of points xy lambda belonging to f naught, such that we have the two norm of y lambda e minus tau e is less than equal to sigma tau. That means geometrically, in the space of y lambda, we are considering a neighborhood of this line, that when we are at this point, say, then we have some value of tau given by this much length from here to till this point. That is your tau value. Fine. And here also you can measure. This is your tau value. Then for the given tau value, you take rho times tau, where this rho is some number in between 0 and 1. So here in this inequality, we get a circular region whose center is this tau e. That means this point tau tau, this particular coordinate, and having radius sigma times tau. So we get a circular region given by, say, this circle for this particular value of tau. And now when I reduce the value of tau, let's suppose my tau is over here, then accordingly I am getting a point over here. Now for the reduced value of tau, sigma times tau is a small value, smaller than the earlier radius, and therefore I will get now for this particular value of tau will give us a circular region with a bit smaller radius. Then for more small value of tau we get a bit smaller radius circle, and in this manner we will keep getting smaller circles. Fine. And ultimately then this entire region for different values of tau will give us a region in between this line and this line, at the bottom this line. Fine. So these two lines, although my drawing is not perfect here in between these two lines the region is the region given by this n2 sigma. Now in a feasible region, let me now draw out the central path. Let's suppose this is my feasible region and here was your central path, which is the image of this line in the set capital F or F naught, and then image of these two boundary lines, let's suppose are these two curvical paths here. Fine. So this neighborhood, this two norm neighborhood essentially gives us a region, the region in between these two curves in the set F naught. And now you consider your iterations to start from a point x naught, y naught, lambda naught, maybe somewhere over here, an interior point interior to this feasible set capital F, and then take the next iterative point, take the step length alpha naught in such a manner that we are not moving out this region bounded by this pink curve and this pink curve. So from here you may take a step maybe till this much amount so that we are not going out of this two norm neighborhood. Then from this point the next iterative point has to be taken. Maybe the next iterative point is trying to move out of this two norm neighborhood, but you control your the value of step length alpha k in such a manner that it is not exceeding this two norm neighborhood. So here goes for this initial point, this much is your step length alpha naught, then this length is your next step length alpha 1, and so on. Fine. So in this manner, by not moving out of this neighborhood, you are a bit controlled. You notice that these two boundary lines are slowly getting shrinked towards the optimum solution, towards a KKT point, and that will then guide you to reach at the end of the day to a KKT point. Fine. So this is how we control the step length alpha. We have also many other possible ways of controlling the value of alpha. You know, by the different choice of alpha here inside this equation and different choices of this sigma k gives us different kinds of interior point methods. And here this entire method is known as the interior point method because we are moving in the interior of the feasible set, and that's why it is named as the interior point method. And the fascinating result on assuring that after certain iteration numbers, certainly the value of tau k is going to be lesser than epsilon, your tolerance level or your precision scalar. The result is as follows. We suppose that xk, yk, lambda k is a sequence generated by the above algorithm, the interior point method algorithm, and you have taken the precision scalar some number in between 0 and 1, and also assume that the parameters tau k they are degraded, but if the degradation follows the following rule, that tau k plus 1 is less than equal to 1 minus delta divided by m to the power omega times tau k for all k starting from 0, 1, 2, 3, and so on, for some positive delta and omega. And then if the initial point satisfies your value of tau naught is less than equal to 1 divided by sigma to the power nu, for a positive nu, then we can prove that there exists a natural number, an iteration number, which is capital O of m to the power omega times the constant logarithm of epsilon, for which you have tau k less than equals to epsilon for all iteration numbers greater than equals to capital K. And in this result, then what is it saying? That if your tau k satisfies this inequation, now you notice that this inequation satisfaction is at our hand, that you take sigma k such a manner that in the next iteration you have tau k plus 1 less than equal to this. Fine. So that's why the sigma k factor was introduced. And now this particular thing, that initial point satisfies this, this is a bit crucial, that you have to choose a point for which this is satisfied. But here you notice that this right hand side is a very big quantity, because if you choose epsilon very small, then 1 by sigma to the power some number, this is a very big quantity. So this condition is not a very crucial condition. And then we notice that then certainly there exists a natural number capital K, where capital K is bounded by a polynomial of the number of inequations, number of constraints in a given quadratic programming problem. After these many iterations, certainly your tau k will become less than equals to epsilon, and thereby proving that your general interior point method that we have stated over here, that certainly converges if your initial point is tactfully chosen and your sigma k is also tactfully taken. For a proof of this result, although I do not like to skip proofs, the proof of this result is not that tricky, but still I did not want to skip some mathematical proofs. But to keep proving results, so we need some time. If I take time, this much amount of time even for a particular method, then the NPTEL authority, NPTEL team will be scolding me too much, that I'm taking too much of time to just explain a particular thing. And therefore, I would request you to please visit the proof of this result, which is not that difficult to follow. It is just a straightforward calculation. You take logarithm on both the sides of this equation, and then afterwards you will get this inequality. You please see the theorem number 6.4.2 in the page number 265 of the book by Forst and Hoffman. Now here, as I have mentioned, due to the choice of this alpha and sigma k, there are different variations of this interior point method. And apart from this, there are also some more variations, that you notice that here we have to choose a point x naught, y naught, lambda naught that is inside f naught, and this is not always an easy task. And therefore here, that we are getting here these values zeros, may not always be possible. We may have some residuals here for this part, that here we have this term and this term. We have replaced these two terms by zero matrices, because of the fact that the point xk, yk, lambda k is a feasible point. But if it is not feasible, then in that case we may have certain residual and thereby giving a flexibility that even if the initial point is not inside f naught, but still a certain convergence result is going to hold. So here a variation in this algorithm will take place when the zeros are being replaced by certain residuals. For getting a deeper knowledge about these interior point methods and their different variations, I would like to refer you three books. These books are not textbooks, they are reference books. Maybe you can consider Dane Hetog's book that I'll be writing here is a textbook that from back to back you can go for reading, but other two books will not be for textbooks. They are just reference books. The books that I would like to refer, they are not again the only references, but the references those I had a chance to visit. This book by Tarlake came out from Springer. This book by one of the giants in numerical optimization, Professor Wright, came out from Siam. And this book, which I was talking about as maybe referred as a textbook, this came out from Fluid Academic Publisher. In this book, authors have detailed nicely the close association of the interior point method with the interior penalty method or the log barrier formulation for solving a constraint optimization problem. In this book, you will find that in how many possible ways, in how many possible viewpoints you can look at to solve the KKT system by reducing the duality gap, the gap between primal and the dual objective function value along the central path. And in this book, you will find a nicely detailed, rigorous mathematical discussion of the primal dual interior point approach. And this book is a completely reference book. Here, all possible variations of the interior point method can be found. There are also some other interior point methods book, like the book by Yanu Ye is one of the famous book, and also there is also other book by Tarlaki and his group. You may just go for Google up the books for interior point methods. You will find several other books. But if you want to sit with a pen and paper and want to learn deeply the interior point method, I would like to refer you this particular book to sit down with and then go from back to back. You will be really enriched with learning interior point approach for linear, quadratic as well as for convex optimization problem. From these discussion or these references, you then have at least gotten an idea that how vast is the optimization theory, how enriched it is now, that just for one method, the interior point method, you have several textbooks, you have several reference books. And not only this is for just the interior point method, for several other methods, like one day I was mentioning about the conjugate gradient method. For the conjugate gradient method, you will find a big volumetric book is there. For the trust region method, there is a big volumetric book, and these volumetric books are there for just only one method for optimization, and therefore it is not really possible to explore each and every method and their details in just one course on optimization. Even for just only one method of optimization, we can have 2 3 complete semester courses. and therefore you can get a sense how vast is the development of the optimization theory. Now here I would now end up this lecture, but before that I would like to mention a very fascinating history on the paths of the development of the interior point method. I have explained here the interior point method for the quadratic programming problem. We have started our analysis for solving this quadratic programming problem, right? But interior point method was not initially arose out for solving quadratic programming problem. It was actually arose out for finding a polynomial time algorithm to solve a linear programming problem. Till 1972, the simplex method, Danzig's simplex method, was only one method to solve the linear programming problem, and that was commonly used. And people have been thinking that the simplex method is possibly the champion forever to solve a linear programming problem. But it was 1972 when Victor Klee, a professor from University of Washington, and George Minty, a professor from Indiana University, they have challenged the efficiency of the simplex method, and they have devised a distorted cube in the n-dimensional Euclidean space, and they have shown that in the worst case, simplex method may take exponential time complexity. And there have been then a quest among the researchers in optimization theory that is it possible to find or to construct a polynomial time method for linear programming problem. Then towards finding a solution to this quest, Khachiyan, Leonid Gendrikovich Khachiyan, one Russian mathematician, when he was just 27 in the year of 1979, he came out with the ellipsoid method, and he has proved that ellipsoid method can solve a linear programming problem with polynomial time complexity. But although this ellipsoid method might be the first polynomial method to solve linear programming problem, although it has a very nice theoretical consequences, but soon after its appearance, it is found that ellipsoid method is hopelessly slow. And this is actually called the gap between theory and practice. It is a kind of paradox. Theory says that it has polynomial time complexity, thereby better than the simplex method, but it is not practically true. And consequently, the quest among the optimization theorists, changed to find a polynomial method for a linear programming problem that is also efficient in practice. Towards this aim, then in the year of 1984, a complete revolution came in the theory of linear programming problem. It was Narendra Karmakar, an alumni of Indian Institute of Technology, Mumbai, who came out with a projective method, and it was claimed that it is a new polynomial method that could solve large scale linear programming problems, and that is 100 times faster than the simplex method. Although this announcement was a bit of exaggeration, but it stimulated very fruitful research activities, that it is really possible to find a practically efficient method that may beat the simplex method. Soon after the appearance of the projective method of the Karmarkar, great optimizers like Gill, Murray, Wright, they have proved the equivalence between the Karmarkar's method and the classical logarithmic barrier method for linear programming problem. And this logarithmic barrier method, it was given in 1960s by Fiaco and McCormick, and that was studied as an interior penalty approach to solve nonlinear programming problems. But as the barrier method suffers from the numerical difficulties of the Hessian matrix, this barrier method became out of date in 1970s. And by the early 1980s, barrier methods were almost universally regarded as a closed chapter in the history of optimization. However, after the appearance of the projective method of the Kormorkar, the barrier method got revived, and it was found that the barrier method has a close connection with the projective method of Kormorkar to efficiently solve linear programming problems. And in the meantime, in 1990s, several optimizers started employing the interior point methods in solving several nonlinear programming problems. And since then, interior point method have been applied to large class of nonlinear optimization problems and are still topics of current research. With this comment, I stop this lecture here. In the next lecture, we shall start our discussion with the numerical optimization methods to solve constraint optimization problems where constraints are given by nonlinear equations and inequations. You notice that so far we have been talking about the optimization methods with the constraints are given by linear equations and inequations. In the next lecture, we will consider optimization methods to be discussed where the constraint set is given by a set of nonlinear equations and inequations. Thank you. Thank you all for all of your kind attention.